If we look at the standard one-dimensional number line, the indivisible atoms of mathematics, primes like 2, 3, 5, 7, and 11, appear as isolated points along a flat sequence. As the line expands, the spacing between them becomes highly erratic. They occasionally form tight clusters, like the twin primes 17 and 19, but these clusters are interrupted by massive barren deserts where no primes exist at all. Classical Euclidean geometry and basic Pythagorean distances offer no formula to predict these gaps or unify this distribution. This creates a mathematical stall point, an analytic proof failure, where the rules governing the number line can no longer describe the sequence. The irregularity we see is a byproduct of the flat, restrictive space we force these numbers to occupy. To find the logic behind the spacing, we must treat prime generation as a harmonic wave emission. We map these signals onto a two-dimensional grid, defining the radius as the reciprocal, the exact inverse, of the gap between consecutive primes. We then multiply the prime by the golden ratio to find its angle. This irrationality acts as a dispersant, ensuring every prime finds a unique, non-overlapping coordinate. Because the radius is a reciprocal, those massive gaps from the number line produce tiny fractions. This math mechanically pulls prime deserts toward the center, forming a dense inner core. Conversely, the most frequent small gaps yield higher values, pushing the points outward to form a distinct ring on the far perimeter. In this 2D space, the harmonic waves of close-spaced primes begin to overlap. These dense clusters undergo destructive interference, canceling out to manifest as quantum nulls, stamped signatures that preserve the data as topological memory. By shifting into complex geometry, the unpredictable jumps of the number line resolve into a symmetrically stable, data-compacted blueprint. This geometry scales further at specific milestones called Fibonacci primes, like 5 and 13. At these points, the system resets its counting logic, switching algebraic bases. Because these shifts in counting logic require more coordinate axes to distribute points evenly, the 2D map is forced to fold. The plane warps upward, expanding into a three-dimensional metric tensor. This creates a physical-like terrain where the elevation of any coordinate is determined strictly by its divisor count. Numbers with many factors, highly composite numbers, create massive peaks and structural friction. But because primes have a minimal divisor count, they represent minimum energy valleys. They form the paths of least resistance that guide the flow of the geometry. This discrete 3D prime topology provides the global invariants that prevent spatial drift, anchoring the continuous fabric of the manifold. The final challenge is routing information across this manifold without triggering mathematical overflow as integers expand. Accurately locating a node in this space requires measuring spectral frequencies rather than physical distances on a map. To translate the prime distribution into these spectral coordinates, the system utilizes the Riemann zeta function. The non-trivial zeros of this function provide the modular resonances needed to map the primes into localized, four-dimensional hash blocks. This spectral data is processed through the Hopf angular routing protocol. This protocol discards flat space addressing tables, embedding nodes onto high-dimensional hyperspheres. Data paths snap into fixed, non-uniform angular sectors, exploiting the natural clustering of the primes to reduce the compute footprint. By resolving the prime sequence as a complex dynamic resonance, we find that these numbers are not random. They are the immutable structural anchors that allow multidimensional routing geometry to converge and stabilize.